Hi. Okay, so can anyone hear me? Okay. I just want to give some couple couple seconds for others to join in, and we can get started later. Uh, so, how's everyone doing? Okay. So, mm, basically, I think we have. I'm not so sure. Which chapter did Dr. Kim talk about, or have he talked about? Did he already talk about logistic regression, or you guys haven't touched that topic yet? Oh, he's doing logistics. Oh my, okay. So I might get a little bit ahead of him now, which is something I don't want to. Hmm. Okay, so in that case, I might just so for today, I'm still going to teach this lab because we still have to keep our schedule. But I'll probably put the assignment a little bit later and the due date later, so you guys can have more time to digest and have more time to uh, think about the homework. Mm, but I think that because like for this one this time I think we don't have to use our hand to do that. So it's not like last time. So we can just simply use R to run it, and basically the most important part is just to interpret the result. And I think it's much easier than last time. Well, last time is not that hard. It's just a little bit, mm, you know, tedious. Just do the hand calculations. Okay, so mm, I think we have a lot of people already. So I will just go ahead and get started. Okay, so today we are going to talk about the logistic regression. And as I said, if you have any questions, if you have any concerns, anything, just let me know. And also, this topic will be covered tomorrow by Dr. Kim. So I'm a little bit ahead of him. So don't worry about that, and just let me know if I need to slow down. I need to like explain something more, so you can better understand it. Okay, just type anything there, and uh, I will try my best to explain. Okay. Okay. So the first question is, when do we use logistic regression, or why we're using that? So um, in some cases, our dependent variable is categorical, or uh, in a more common way, we often have like a dependent variable which is binary, which is like binomial. So it's like literally like zeros and ones. So in this case, it is kind of hard for regression, just the basic multiple regression or simple regression, to capture the variance, right? Because it's just zeros and ones. So instead, we are using a linking function, which we can describe the relationship between the y and x, the predictors, um, in terms of probabilities. So here we're using probabilities to predict like the group membership, uh, which means like 0 or 1. The dependent variable is a binary variable of having disease. For example, this is an example. So the dependent variable is binary of having disease, which is 1, or not having disease, which is 0. We can predict the probability of a patient having disease given values of sets of predictors. So here we can quantify our probability by this symbol pi, which is a population parameter. The pi equals to the number of events that happen, or and divided by the total number of outcomes. Okay, so this is the probability, the definition. And then we have two more terms. So you can see that those two terms later on in our regression term, in our equations. So for odds, it's just the pi divided by 1 minus pi. Okay, so it's like the probability of an event happens divided by the probability of event that does not happen. This is the odds. And the log odds is the logarithm of the odds, which in a lot of cases it is termed as logit. So you can say that the logit is just the log of odds, okay, the natural log of odds. Okay, so how do we model the probability? So as we said, it's the a set of predictors predicting the probability, right? So actually, we're just using a logit function to model probability. And you can see here, a logit function looks like something like this. So this e to the y divided by 1 plus e to the y here, this one will return a probability for us. And this y here is equal to a linear combination of predictors, just like the multiple regression, right? If you can see this part, beta 0 plus beta 1 x1 plus beta 2 x2 plus and to beta n xn. So you can see here this equation this combination, it's substituting y here to become like here and here. Okay, so if we have this equation, our this pi x, this one will become the probability. Okay, so that's how we capture the probability by specifying a logit model with our predictors in it. Okay, and then so there are some good features of logit function. The major one is that, well, for the multiple regression, as you know, that is not bounded. The regression line is just a infinite line, right, from the negative to the positive. But the logit model has two asymptotic line. One is like zero at 0, the other is at 1. So this little picture is not so accurate, right? But it is bounded. So the y is bounded between 0 and 1. So in this case, we can just capture the probability here, right? So because probability is bounded between 0 and 1. So that's the one thing we like for the logit function. The second feature we like to use that, it is because when we take the log here, which is also called a logit transformation, and you can see here that this part of the equation here, it becomes the log odds, which is also called the logit. And for here, on the right hand side of the equation, we have our normal multiple regression equation, like the linear combinations of predictors here, right? So basically, from this part, the last equation, you can see how things work out, right? So you can just interpret those beta 1, beta 2, or like from beta 0 to beta 1, beta 2, those coefficients in terms of logit, which is the log of odds, right? So for example, one, if you have an estimate of the beta 1, you can say that in 1 unit increase of x1 will result in how much, like beta 1 or b1, sorry, like just a number, right? For example, 0.05 or 0.056 increase in the logit of y, right? So you can say that. So here in this transformation, after this transformation, you can easily interpret the model coefficient. Okay, so this is these are two good properties of logit function. Okay, so why we cannot directly predict probability? So if we predict probability as we conduct a regular multiple regression, we need to use the OLS to estimate parameters, but the ordinary least square regression is unbounded, like we said, unbounded, right? So you can predict a probability is greater than 1 or even negative. So this is definitely not the thing we want, right? We want our probability to be bounded. And if the dependent variable is probability, so we have 3 assumptions from the ordinary least square will not be satisfied, right? So the residual will not normally distribute it, and also the residual will not have a homogeneity of variance. This is something we don't want, because our residual is violating the assumptions that it's necessary for the multiple regression, the regular least ordinary least square regression. So we used to have this linking function, which is a logit function, to link our set of predictors to the probability, right? So you can also say that the this kind of linking function is called a generalized linear model. Okay, generalized linear model. So in this lab in R, we're just going to use GLM. So in the past, we are all using like the LM function, right? LM. But at this time, we're using GLM, which is generalized linear model. Okay. Okay. So let's look a little bit deeper into the equation. Okay. So here we have three forms of the logistic regression equations. I think you are just you are familiar with the let me see, like the first one or the third one maybe. We can just leave our second one a little bit later, but let's look at the first one. Okay, so the first one is easy because that the outcome is a probability. So we have a very, we all have common sense what is the probability, right? So probability is it's bounded between 0 and 1, and you can interpret this probability very easy, right? But on the right hand side, this equation is kind of hard, right? So in here you cannot say that like for example this x1. Okay, so holding other predictors constant, the increase of x1, like one unit increase of x1 will result in how much probability will come of y increase or decrease, right? So in this case, there is no a straight relationship between the you cannot just directly interpret the parameters here. Okay, so that's something a little bit tricky. Okay, so this is just the first one is easy because of the y here. Okay, the second is a this is a odds function, so the left hand side is the odds. Okay, so you can see here we transform this probability into the odds, which is the probability divided by the probability that is not happening, right? So this p hat divided by 1 minus p hat. Okay, so but on the right hand side, it's still kind of hard to expect, right? So it's e to the combination, right? It's e to the combinations here. So this is kind of like a middle stage, and you could interpret the outcome in terms of y, in terms of odds. Okay, odds as outcome, but not a lot of people have a common sense of like odds here. Okay, so this is probably like a middle stage. Okay, so the third one, as you can see here, our right hand side, it's very, very meaningful here, right? We can directly interpret our right hand side and look at our y here. oh, we just talked about like in the previous page, right? In the previous 2 pages, 2 slides before. So on the on the left hand side is the log odds, which is also called logit. Okay, so in this case, you can directly interpret the parameters, the coefficients, you know, in terms of logit. So that's how the relationship between the predictors and the probability of the outcome. Okay, so all three equations are essentially the same. So the R output will give you the regression coefficients of the predictor based on the third equation. Okay, so based on this logit model here. So when you're plugging to your function, to your equation, you need to choose this number 3 here. Okay, and you can just put it back. If you have those estimates, you can just put it back by just like going backwards to form your uh, number 1 here, like the equation in number 1 here. So your y will become the the probability, and on your right side is the equation that involves the your estimates for the predictors. Okay. Okay, so you can see here for interpreting the intercept and the partial regression slopes, which is our coefficients. So for the intercept, it means that the value of the log odds here, which is a logit, when x1 equals to x2 equals everything equals to 0. So everything equals to 0. What is the what's the logit of y? Okay. So B1 is like for 1 unit of increase in x1, what is the increase in logit in y? Okay, so this is the value of the increase or decrease in the logit in y. Okay, so far we have finished the introduction of the logistic regression, and let me know if you have any questions or is there any concerns or anything that is not clear. Okay. So moving on, we have several model fit indices to evaluate our model fit of the logistic model. However, here we need to pay attention that the traditional model fit indices will not work in here, especially R square or like the F test for the R square. Here we are using some other forms. Okay, so the first one is chi-square goodness of fit test, which is I think is related to the likelihood ratio. I think that those two are identical when we talk about the model comparison. Okay. The second one is pseudo R square, and the third one is AIC and BIC, and the fourth one is correct classification. Okay. So let's look at the first 4 and then we'll look at the last one. Okay. So for the model fit, the first one, model fit, okay, so our null hypothesis is the full model is not significantly different from the null model, and the alternative is that the full model is significantly different from the null model. Okay, so this is a chi-square goodness of fit test. We're going to see that later. The second one is pseudo R square, because why it's called pseudo R square? It is because that there's no such fit indices to describe the proportion of variance account for, because our variance is either 0 or 1, right? So our variance is kind of weird here. So there's no such sense here. We have to. So there are a lot of researchers developed a lot of different forms of pseudo R square for us to use. So, but it is mm, in this case, we have to distinguish. We have to evaluate those indices based on the literature. So there are like in SPSS there are like Cox Schnell and a lot of other R square indices, but in the R we have another one which is called McFadden's R square. So here we're using this one, but so the interpretation here will strictly only based on this this person's this researcher's literature. So we are going to see that later, but just pay attention to how unique each pseudo R square developed by other researchers it is. Okay, how unique it is. So I personally I think that we have better indices for us to evaluate a logistic model, a logistic model. Pseudo R square, I think it's just it's kind of hard for us to communicate. You want a similar term, no matter like always, no matter it's like regular multiple regression or like logistic regression. But this just pay attention that the pseudo R square is not a regular R square we can think of. Okay, maybe it will behave the same, in terms of some properties, but the interpretation is definitely not the same. Okay. And also, according to this paper, the logistic R square measures for good logistic models are generally smaller than R square of good models in the ordinary least square regression. So this may lead to misconceptions, misperceptions of the logistic regression results as indicating poor models. Okay, so you can see that later, but I think in our example, our pseudo R square it's very small, so it might indicate some bad model fit. Okay. Okay. So this is a pseudo R square, which is the second one. The third one is called AIC or BIC. So this is information criteria. Okay. So for the information criteria, we have two kinds, which is a little bit different in terms of their calculation. So generally, we don't have a guideline or a cutoff for the information criteria, but the general sense is that the numbers should be as lower as possible. Okay, so it should be the lower the better. Okay, and you look at here. Just hold on 1 second. Got it. Okay, so we use AIC or BIC to, or we can use those to compare models. So we can use that to either select a to select a model with either fewer predictors or more predictors in our model. So this is also a model comparison indices, but and the idea is simple. It's just then if we have a lower values of AIC or BIC, uh, we can say that we have better model fit. Okay. So hold on a second. Phone is okay. Okay. So as we said, uh, besides the AIC or BIC, we can also use the likelihood ratio test. So for likelihood ratio test, it's just the same as the likelihood. It's the same as the chi-square goodness of fit. Okay, and we are comparing two nested models, and here the model comparison is sort of like the R square, the F test for R square change. Like if you think about testing for interactions or like that, it's like two nested models, right? We're comparing two nested models, which we're doing similar things here as well. So there is a term called deviance. So it is calculated by the -2 times the likelihood ratio, and the deviance of the first model divided by the minus the deviance of the second model, which have more predictors, which is the full model. The null model, the deviance of the null model divided by deviance of the full model follows a chi-square distribution. Okay, so using this likelihood ratio test, we can also use that to decide whether we're going to choose a simpler model. Okay, we'll choose the full model or a null model here. Okay, so this is the last, not the last, but one of the ways to do that, to evaluate the model. Okay, the last one is I think it's making most sense, is the correct classification. Because we are using logistic model to capture the probability, right? If we are going to use that to predict our results back into zeros and ones, we have our prediction result, right? So here is an example of the you can see. I think this matrix is very commonly used. So this matrix is called confusion matrix. So we can use the confusion matrix to calculate our accuracy here. So if you see here, if the actual result is either guilty or innocent, right? So here, witness classification, we can see that as for example, predicted value, right? So predicted value is also either guilty or innocent. So if the actual is guilty and our prediction is also guilty, we have true positive, right? It's a correct decision. And if the true is innocent and we predict it's innocent, we have the correct rejection, which is also a correct decision here. So the accuracy refers to the guilty and the predict guilty, and the innocent predict innocent, right? Those two we just added those two values divided by the total number of observation, we can have our accuracy value. So that is called the percentage of our correct classification. Okay, so by random guessing, we in theory we have like 50-50, right? We have 50%. So if the model is predicting less than 50%, we can say that if this model is not better than random guessing, right? Random assignment. So that's how we decide, like in this case, in the terms of accuracy, right? Right? How the model, how well the model is, or how poor the model is. Okay, this is the last one. So let's move on to our example. Okay. So in our example, we have 31 observations, and we have 3 variables here. I'm not so familiar with American football, so I have no idea how to interpret the at least I don't know how to interpret the good and the yards. Uh, I I wonder if anyone can help me with that. Mm, I know that like the home is like the zeros and ones refers to the away team or the home team. Uh, but for good, the good variable, I don't know what does it mean. Like what fail and a good in this case. Okay, in terms of football game. Mm, I might just interpret that as like a score or something, or like a result. And the yards is a continuous variable definitely, and I think that refers to the scoring system, or the how the field looks like. Uh, but anyway, we have okay. We uh, Anyway, we have our 3 variables here. So we are using the home and the yards to predict this good variable. Okay, so as you can see here, we have our dependent variable, which is a binary variable, and for the complete versus incomplete passes, I guess a good versus fail is actually win versus loss, or touchdown versus no touchdown. Oh, okay. Okay. The complete versus incomplete. Okay. Yeah. Well, I sort of guessed that, but I haven't. Me too. I have no idea how the football. I just I think I went there, to the stadium once, and I just like cheer with others, and I don't know what happened, to be honest. Um. Okay. So just feel free to interpret that, because I have no idea. I checked, and the rules are just a little bit too much for me. Uh, and maybe I will spend some more time to understand. Uh, okay. So it's in a distance, so whatever the catch is a legal catch. Okay. Oh, okay. Which is a binary variable, right? We can also be representing your field goal attempts. Oh, okay. So, um, Okay, so how about let's just move on because we can choose either one, like either like complete or incomplete catch, or a good kick versus a failed kick, or like a field goal attempt, a failed field goal attempt, or a good field goal attempt. Okay. Yes, yeah, the interpretation will be similar. So that's not a problem for us in this case, and feel free to interpret that. But I checked the football data. This data set, well, I got it from the previous TA, and this data set, I don't think it's in our textbook. So anyway, uh, let's move on. Okay. So it is the time for us to open our R Studio. Okay. So this time we need to install some of the packages. Here is the code clear. I think it's okay, right? Okay. So we have to install some of the packages, and we need to run those, and to import the data. Okay. And in our data set, as you can see, we have three variables. The first one is good or failed here, and this is the home team or away team, and this is the yards. Okay. Okay. So first, we are going to generate a generalized linear model, which is our logistic regression, right? Logit model here. So we're using GLM in this case, and you can see here we have our predictors, and like the two predictors and our outcome here. Good. Okay. So family, we set the family into binomial, and the link here is logit. Okay. Well, you don't have to necessarily write this link equals to logit. It's just like you can just delete that, but it's fine. Just put it there. It's okay. And the data is the data set we have here. Okay, so let's run this. Okay. And we can see our summary and the confidence interval. Okay. So in the summary of the model, what you can get is the estimates of the parameters, right? You can have the estimates of the intercept, the constant, and our beta 1 and the beta 2. So beta hat 1, beta hat 2. Okay, and their corresponding z value and p value. Okay, z value I think is a walled z test because we're not using the t test anymore. We're using the z test, and here we have our values here. You can see that none of the predictors is significant. Okay, so we don't have a good model here, and we cannot tell, but we don't have some significant predictors here. Right? And here we have our 95% confidence interval for the intercept, the first predictors and second predictor. Okay, here is the confidence interval, uh, and you can see some of the information for the likelihood ratio test, but it's not showing that clearly. So that's why we're using some packages, and also you can see the AIC value, right? Okay, so this is where you get the parameter estimates and the confidence interval. Okay, this is the first step. Okay, the second step, we are examining the model fit. Okay, so there are one, two, three, four ways to check our model fit. Okay, so first one is the chi-square goodness of fit test, which also just the ANOVA test for the general linear model. So if you're in the help page, you can search for ANOVA.glm. So this will give you the the specifics. So we are actually doing the analysis of deviance for generalized linear model fits, right? And we are using the chi-square test to test our significance, and our null model here is just the model without any predictors. Okay, if you run it, you'll see that this is our null model, this is our full model, and here is our deviance, and this is the significance here. You can see that in the slides as well. Oh, where's my mouse? Okay, so you can see the slides as well here. So the model proposed does not deviate from the null significantly. So the standard deviation is 2, and this is our chi-square value, and this is the p-value. Okay. 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 So how about we just talk about the interpretations of the coefficients at the end? Okay. We're just going to continue for the model fit. Okay. So after this chi-square goodness of fit test, we can see the model fit test. The second one is the pseudo R-squared. So by using pseudo R-squared, we're using this PR-squared function, PR2. Okay. Okay. So we have a bunch of information here. I didn't really look at very closely into R-squared ML or R-squared CU. I'm just going to choose this McFadden one. Okay. So for the McFadden one, it is defined as the oh, this is something not so correct, right? Let me see. Where is the equation? Just give me 1 second. Let me fix this. I think I write it down in MacBook, and it turns out to be kind of weird. So I think this is just only a minus sign. So it's 1 minus the natural log of the L1 and the natural log of L0. So L1 and L0 are the likelihood for the full model, the fitting model, and the null model respectively. Okay. So this is how you calculate the McFadden's R-square, and the smaller the value indicates a worse model fit. Okay, so in this case we have very small value here. So overall, we don't have a good model fit. in this case. This is how you interpret the pseudo R square here. And the next one is the AIC or BIC. So in our summary, you can see that, right? We already have the AIC value. And for the BIC, I'm just using this BIC function to call out the BIC. So you can see there's a little bit difference, but the BIC, I think, is more stringent or more conservative than the AIC. And that's why you see a bigger value. Okay, so the smaller the better. So BIC is even worse, right? Okay, so since we don't have a clear guidelines for here, we cannot tell much more, but we can see those values are quite big. Usually it's not that big. It's like sometimes even negative, right? So this is not something that we don't want to see. Okay. The last one, sorry, not the last one, but and the next one is the correct classification, which is the accuracy. So using this confusion matrix function in the package reg class, so you can call out the confusion matrix for this model. Okay. Oh, okay. So here, the selected parts. Okay, here is the confusion matrix. You can see here our true positive. Sorry, this is true negative. True negative is 14. True positive is 1. So together we have 15 correct numbers of prediction, right? And our total is of 31. So that gives us a percentage of correct classification of 48.38%, 39%. So it's like even less than the 50% random assignment, random guessing. So it's a bad model in this case. Okay. For the accuracy, you can calculate like this way. This CM11 is just mean this 14 here. The CM22 is this 1. CM33 is this total number of observation. And I timed 100 to become a percentage. There are other indices like sensitivity, specificity, another one, I forgot the name. It's all calculated based on the confusion matrix. Okay, so if you have experience in machine learning, you'll be familiar with this, right? Because the classification is one of the most important goals in the machine learning, right? So this is something you will see there very often, but let's just calculate accuracy in this case. Okay, so last part is a model comparison. For the model comparison, we're doing the likelihood ratio test, and also you can just you can check the AIC and BIC. But in this case, we're just gonna look at the likelihood ratio test. Okay, so we are going to use this LR test, likelihood ratio test function. First, let's see our this is the same we see in the chi-square goodness of fit test, which is essentially the same, right? And also we can do something different, right? We can run this model 2. This model 2 is just the dependent variable predicted by this only one predictor here. So how will that be? Right? We're comparing the model 2 with our full model, model 1. Okay, and as you can see here, the full model is not significantly different from the first model, the null model. So they are sort of similar here. Well, generally speaking, the model is not making much progress from the from the from this model 0, right? This, so even you doing this likelihood ratio test, that does not make much sense here. But it will make sense if you have a lot of predictors and you want to screen out some of the predictors. You want to have a simpler, clearer model. Right? So you can do that to do the nested model comparison here. Um, okay, so let's get back to the summary of the model to see the interpretation of the coefficients in this case. Okay, so how about let's just go back to the slides. So here, okay, oh no, not here. Okay, here in slides 13. Is that 13? Yeah. In slides 13, you can see the equation and the interpretation. Okay. So on the left-hand side, since it's a logit model, we have the logit of y, and we have our on the right-hand side we have our predictors. So you can just plug in the estimates for beta 0, beta 1, beta 2 here in this case, right? However, if you interpret those values, like for example, this negative 0.578, it means that the logit value of y, the logit value when every predictor is set to 0, right? So here is another interpretation. So everything here, you can see down here, are some interpretation in terms of odds. Okay, which is the you can see that which is the second stage here. Okay, I think this part is made by the previous TA, and I think she wants to give you some like other perspective in terms of odds. But I don't think I think it's okay, but there's no well, it's good to show here so you can have a sense of like how to interpret the results, interpret the parameter estimates in terms of odds, and this is how you represent it. But strictly speaking, you can just interpret in terms of logit, right? That's much easier. Like for example here, 1 unit increase in yards will result in 0.01 logit increase in y. That's in good, right? That's much easier to interpret. Oh, sorry, holding other predictors constant. Okay, holding the home constant. I missed that sentence. That is very important. Like holding or like controlled for the other predictors. 1 unit increase in yards will result in 0.01 logit increase in good. Okay, this is how you interpret in this simple. This is very clear equation here. This is how you interpret that in terms of odds, and you can just use like the first equation to interpret that in terms of probability, and that is something you need to rephrase it, right? You need to rephrase it. You can say that holding other constant, holding other predict when we are using like probability terms, you say like holding the predicted home constant for 1 unit increase in yards, the probability of this is increased by, you need to calculate it like here. Okay, so it's not that hard, but you need to calculate the probability here, right? The increase of probability based on here, which is exactly what you're doing for the odds equation. Okay, so this part might be a little bit confusing, but how about let's just focus first, just focus on the logit model, which on the right hand side is very simple. It's our like multiple regression form, right? And the left hand side is the logit. So in terms of interpretation, it's better to give me the interpretation in terms of logit in our outcome than the probability or the odds. You know, it, I will look into the homework a little bit more to see if the homework requires you to use one of the more interpretation than just one interpretation. So I think this one is sufficient. Yeah. So, but it's good to know how to interpret that in odds and the probability, because those three forms are essentially the same, right? It's just the same. Okay. Unfortunately, the R, I don't think the R will give you like other estimates. Right? It just give you this estimate, so you have to interpret that back into odds or probabilities by this way. Okay, so I think that's it for today. Any questions so far? If not, let's just end this live stream and see you next week. Okay. Take care. Bye.